Hi everyone, welcome to the Tutte Colloquium. I'm happy to introduce Arnesh Sujanani, who's a postdoc here, started this fall and works with Walla, Stephen, Henry, and Saeed. So he received a PhD in operations research from Georgia Tech in 2024 under the supervision of Renato D.C. Montero. Yeah.
Okay. Yeah. Thank you. So I'll be presenting on this inexact augmented Lagrangian method. I'll go over some optimal iteration complexity bounds and things like that. And then I'll talk about how you can use this to solve large semi-definite programs. So this is joint work with Saeed, Henry, Diego, and Montero. So the first part of this talk, we consider just this linearly constrained convex optimization problem. Minimize phi subject to these linear constraints, and phi has this special structure that it can be written as PCIS plus PCIN, and PCIS is smooth and PCIN has nice proximal mapping, but I'll talk about all of these terms later. And then the second part of the talk, I'll talk about semi-definite programs, which is actually just a special case of this P, and I'll define all these things, like this delta N is the spectraplex. And so first I wanted to go over some background on historical developments in complexity theory, because the first part of my talk will be talking about complexity theory for solving P, and then I'll talk about SDPs, but from more of a computational point of view. So just in case people don't know, I want to go over some historical developments. So first I want to talk about just unconstrained optimization, where you minimize a smooth convex function. So convex function is a function that lies above its affine minorance. And we assume here that the gradient is Lipschitz continuous. So there's this very simple algorithm that's been studied for a long time, gradient descent. And essentially, you iterate as follows in this equation. You move in the negative direction of the gradient, and alpha k is your step size. So gradient descent with step size alpha k is 1 over L bar. You achieve this worst case complexity bound. So you can bound your iterates in this order of 1 over k, this function gap between f of xk minus f star. So if you're given some tolerance epsilon, gradient descent finds a point xk satisfying f of xk minus f star less than epsilon, and at most 1 over epsilon iterations. So this I'm sure most people know. So we call this a worst case or upper complexity bound. But can a gradient method achieve a better rate? And it turns out that you can. So now I'll go over something called lower complexity bound. So we define a first order method to be a method which updates xk as follows. You take some x naught, and the xk must lie in the span of the gradients. So you just use first order information. So Nesterov in 1983 proved this bound that for any k small enough, you cannot make the function gap smaller than 1 over k squared. So the best possible worst case bound one could hope for first order method for the class of smooth functions is 1 over k squared. So can a first order method achieve this rate? It turns out it's yes, from this classical theory by Nesterov. So what is this Nesterov accelerated gradient descent that everyone talks about? It's a bit more complicated than gradient descent. Essentially, you generate this sequence of points x tilde k, which is a convex combination of some of your previous iterates, and then you move in the negative gradient at that point, essentially, this x tilde k. And it turns out you can prove that you achieve this better rate of convergence with step size 1 over L bar. You can bound the function gap. So xk is the iterates that you generate, f of xk minus f star, and you get this upper bound of 1 over k squared now. While before you get 1 over k just for gradient descent. So the iteration complexity for finding a point with small function gap is epsilon to the minus 1/2 iterations. So this is just classical theory. But I think that maybe not everyone is familiar with complexity guarantees for making gradients small. So we say a point x star is a stationary point if the gradient at that point is 0, and it turns out convex functions have this nice property that stationary points are global minima. So a natural question to ask is that given some tolerance epsilon greater than 0, how many iterations does it take for a first order method to find a point such that the norm of the gradient at that point is less than epsilon? So like before, with the function gap, gradient descent finds a point in at most epsilon to the -1 iterations. But it turns out that unlike before, Nesterov accelerated gradient descent actually finds a point in epsilon to the -2/3 iterations, which is worse than the bound it achieved for a function gap, epsilon to the -1/2. And so the natural question is, can you devise a first order method that makes gradient small in epsilon to the -1/2 iterations? And the answer is yes, but it's not exactly so straightforward. So Nesterov 2012 says that he came out with this survey paper. He said that it's hard for a direct method to achieve this bound for making gradients small. So he proposed this kind of proximal point type method, or this regularization type method, to achieve a near optimal bound. So he proposed you minimizing a perturbed version of the objective. So you add this quadratic, and x0 is just some point. And delta, turns out, is your strong convexity parameter. So instead of solving a convex problem, you solve a strongly convex problem with a certain tolerance. So Nesterov AGD can find a point with small gradient of this function, like such that less than epsilon over 2, in this number of iterations, square root condition number times log 1 over epsilon. And you see this delta shows up in the condition number because this function is strongly convex. Delta is strongly convex. So it turns out if you take delta small enough, then you actually found a point with small gradient by using triangle inequality. So if you took delta to be epsilon divided by 2d, where like 2d is like the d is like the diameter where the iterates essentially like lie in, then you do this manipulation and you get the norm of at xk is less than epsilon. And so it turns out you get this complexity of epsilon -1/2 log 1 over epsilon by plugging in this formula for delta in that bound square root L divided by delta log 1 over epsilon. But the natural question to ask is, can the log 1 over epsilon in the complexity be removed? Because people have proved lower bounds for gradient norm minimization, and the optimal complexity is epsilon to the -1/2. So can I remove this logarithmic term is a natural question to ask. So actually it turns out that this question is actually very difficult to develop a method that finds a point less than epsilon and at most epsilon to the -1/2 number of iterations without this log term. So 9 years passed and Nesterov figured this out. But his scheme is a little bit complicated. You have to run n iterations of some optimal gradient method for minimizing the function gap, so you can use his AGD method, but then you have to run n iterations of this optimized gradient method, which is a method that was developed using computer-assisted proofs, using some kind of performance analysis, and you can get a point that makes gradient small in epsilon to the -1/2 with no logarithmic term. The downside is you have to supply these number of iterations n in advance, and it depends on some complicated things. George Lon at Georgia Tech, he wanted to see if he could do it without supplying these n number of iterations in advance. And he was able to do it. He developed a parameter-free inexact proximal point method, which he calls this AR method, which achieves a point with small gradients in epsilon to the -1/2 iterations. And he had to do some very careful technique of how to change the proc center and change the regularization term in the quadratic. And he was able to not have this logarithmic term. So now I'll talk about the problem that I really wanted to study, It's not unconstrained. I have these linear constraints. And so essentially I'm minimizing this PCI, which can be decomposed as PCIS plus PCIN. So PCIS is a convex real-valued differential function that's L bar smooth. So the gradient is L bar Lipschitz continuous. And PCIN is some proper closed convex function. And I have to assume that the domain is compact. So the diameter of this domain is finite. And here A is a linear transformation, and B is just some vector in Rm. And I assume this strong duality condition holds, so I assume that there exists an optimal primal dual pair satisfying 3, and such that, that the primal value is equal to the dual value, objective value. So now I'll talk about like what's been done for this problem. Turns out like even though convex optimization has been very well studied from a complexity point of view, there's still some open questions that I wanted to see if I could figure out. So this paper by Yang Zhu considered this special case where a PCIN is just the indicator function of a closed convex set. So you're just adding an additional constraint. And he proves this lower complexity bound for finding weak primal solutions. So Z star is just a primal solution. So he's not finding an approximate KKT point, but he showed this 1 over K lower complexity bound. And he was able to establish matching upper complexity bounds of 1 over epsilon for finding primal solutions. And same with this other paper in 2019. But again, this depends on like a function gap and primal feasibility, but much less studied is the complexity of finding approximate primal dual solutions or KKT solutions, which is a stronger notion. So finding essentially a solution where I inexactly solve this KKT system in 3. Now so these methods that they developed that achieve these bounds were augmented Lagrangian methods. So I want to talk about augmented Lagrangian methods now because that's what my talk is mostly about. So I just want to talk about how it was derived just quickly. So you can write your linearly constrained problem as an unconstrained min-max problem, as in 4. And it turns out that the max function is highly non-smooth. So you smooth it by subtracting a quadratic. And you can actually analytically solve this max function by taking gradient and setting equal to 0. And when you solve this max function, you get this update in 6. And when you plug in this update in 6 into equation 5, you get this minimization problem. And this function that we have in 7 that shows up, this is the augmented Lagrangian function. So you can really think of augmented Lagrangian function as a proximal point method in the dual, since you're adding this quadratic in 5. So there's many different ways to derive it. So this is the augmented Lagrangian method. To get your next primal iterate, we minimize the augmented Lagrangian function, this function 8. And then using this Z bar that we got from the minimization, we perform the dual update in 9. So the difficulty is that this minimization problem in 8 is often very difficult to solve or cannot be analytically solved. So inexact augmented Lagrangian methods generate their next primal iterate by inexactly solving 8. So they generate the Z bar that inexactly optimizes the augmented Lagrangian function. But there's also this thing called inexact proximal augmented Lagrangian methods. They generate their primal iterates Z bar that approximately minimize the augmented Lagrangian function plus this extra quadratic term. So they make their subproblem strongly convex. So you see this analog from what in the unconstrained case, essentially. So there's these two different types of methods. And why do people do this? There's different reasons, but like in the unconstrained setting, this prox technique was performed to achieve better complexity bounds, as you will see. So what is the solution type and what is the goals of what I'm trying to do? So if suppose you're given these functions that satisfy our assumptions, strong duality, smoothness, etc., and some tolerance epsilon greater than 0, my goal is to find an approximate primal dual slash KKT solution. So I want to find this triple Z, P, and R such that R is in the subdifferential, or gradient plus subdifferential is just a generalization of gradient. And I want this norm of this R to be small. And I also want primal feasibility to be small. So how will I express my complexity results? So complexity results are typically expressed in terms of the number of subproblems of the form in 12 that need to be solved, because you assume that PCIN is a nice function, that these subproblems in 12, which will show up in the algorithm, can be exactly solved. And we call such an operation a resolvent evaluation. So it turns out like every time a resolvent evaluation is done, a gradient evaluation is also done. So this is like a natural way to express complexity. And we also call an AL method parameter dependent if it depends on L bar, which is the smoothness parameter, or the size, the norm of optimal dual multiplier, or the diameter of the set. So given a tolerance epsilon greater than 0, our goal is to develop optimal inexact augmented Lagrangian that achieve this 1 over epsilon number of resolvent evaluations, and also for it to be parameter free and not require knowledge of any of these parameters. So I tried to put as many papers as I could, summarizing what's been done in the past, their complexity results, and if they're parameter free or not. So as you can see from the first subsection, the first 3 methods, they're all proximal augmented Lagrangian methods. They add a quadratic and they minimize a strongly convex augmented Lagrangian subproblem. And they achieve this complexity of epsilon to the -1 log 1 over epsilon. So they all achieve that bound. And I wanted to see if I could remove the log, essentially, like how George Land did for the unconstrained case. Meanwhile, all these augmented Lagrangian methods achieve these worst bounds. Among them, the best bound that was achieved was epsilon to the -4/3. And none of them are parameter free. They depend on different parameters underlying the problem. So I was able to get this complexity actually of epsilon to the -1, which improves just for augmented Lagrangian, not proximal augmented Lagrangian. So from doing like more careful analysis, you actually see you don't need to add this quadratic to get this improved rate. And 2 of my 3 methods are parameter free. They don't require knowledge of these different parameters. So this last method, I assume a stronger condition, the strong duality. I assume some kind of Slater type condition, which I'll discuss. Maybe it's not the best word. And you get some better convergence kind of results. So I first developed this augmented Lagrangian method, which performs epsilon -1 resolvent evaluations to find approximate KKT solution. And this improves on the best known complexity of epsilon -4/3 for an inexact augmented Lagrangian method. And it improves on the complexity of epsilon -1 log 1 over epsilon achieved by a proximal augmented Lagrangian method. And that first method that I have that I call OAL, it's not parameter free. It depends on the diameter of the set. So I developed this kind of restarting augmented Lagrangian method, which is fully parameter free and doesn't require knowledge of this diameter. And then under some stronger assumptions, some interior type condition, I develop a more practical parameter-free augmented Lagrangian method that also achieves this bound of epsilon to the -1. The first 2 methods are not necessarily as practical as the last one in different ways that I'll discuss, but they're just more for like theoretical complexity results. And I also get this complexity on the last iterate, while for the first 2 methods, my complexity is on the best iterate, and I'll discuss all these different notions as I go along. And I'm able to use adaptive tolerance for solving the augmented Lagrangian subproblems and adaptive penalty and with these provable guarantees. Recall this is the problem that I want to solve, convex minimization subject to linear constraints. So I inexactly solve the augmented Lagrangian subproblem. Then I do the dual update. So the question is, how do I inexactly solve the augmented Lagrangian subproblem? We developed this modified version of the AR method in George Land's paper, which I'm currently working on to inexactly solve equation 13. So what does the AR method output when applied to the augmented Lagrangian subproblem? It delivers this approximate stationary point for the augmented Lagrangian subproblem. So if you write the gradient of the smooth part of the augmented Lagrangian function, this LCS, you see that it produces this pair ZK-RK that satisfies 15, so approximate stationarity, and it does this with this complexity because the smoothness parameter of the augmented Lagrangian function is L bar plus the penalty parameter times the norm of A squared. So here's the method formally stated. So this residual ZK is actually the norm of primal feasibility. So I stop the method when primal feasibility is small. Because in 6, I called the AR method with a special tolerance, this minimum of epsilon and C epsilon squared 4D. I needed this to get the convergence analysis to work out. So as you can see, the method is not parameter free. It depends on this D, which is the diameter of this set. So I'm always driving, the RK to be smaller than epsilon by calling it with this tolerance minimum epsilon C epsilon squared divided by 4D. So it outputs this ZK RK, and then you construct this residual, which is primal feasibility. And then after you do that, you do the do update, and then you go to the loop in line 4, and you check if primal feasibility is small. So what are the complexity results? So I call these outer iterations the ones indexed by K. These are the ones done by the augmented Lagrangian method, while inner iterations are the number of iterations the AR method has to do in line 6 to approximately minimize the augmented Lagrangian subproblem. So essentially, you perform at most this number of outer iterations. You can prove this to find a triple that's an approximate KKT solution. So in other words, you get this to hold. So you always have this for all the iterations generated. The RI satisfy this. I'm always driving the RI down to epsilon. So like you could think of this like as a dual algorithm. And then the minimum of the feasibilities is less than epsilon in this number of iterations. So I'm getting convergence on the best iterate, not necessarily the last iterate. And people do different things. Sometimes they get convergence on the ergodic iterate. And the number of resolvent evaluations performed by the AR method during each outer iteration is just this. So use the complexity bound from the AR paper, and then you plug in the tolerance, and you get this bound. So how do you get a good complexity bound? So in the convex setting, augmented Lagrangian, you can take a static penalty and still get convergence. But in all the papers, to get a good complexity, you need to take the penalty on a certain order. So if you take C, which is the penalty parameter, on the order of 1 over epsilon, then you see that the number of outer iterations K you perform is actually just order 1 because you get this cancellation. And then you plug in 1 over epsilon in this other bound, and you'll see that the total number of iterations you have to perform is 1 over epsilon. So you get 1 over epsilon times order 1 outer iterations. So this is the total complexity result. So if you take the penalty parameter on this order, 1 over epsilon, then it holds that you perform this number of gradient evaluations. So this just means you perform 1 over epsilon total gradient / resolvent evaluations to find an approximate KKT point. But it depends on this diameter, so it's not parameter free. So the question is, can we develop a parameter free method that also achieves 1 over epsilon complexity bound? And also, I would say that this method is not necessarily the most practical, because in practice I might not want to take the penalty so large. I might not want to take it to be 1 over epsilon. So in a future algorithm, under some stronger conditions, I develop a method with adaptive penalty. So here's this restarted method that requires no knowledge of the diameter. So what you do is you start off with some initial guess for the diameter, this t hat naught. It's essentially, this algorithm is just a restarted version of the previous algorithm. And you call the AR method with this tolerance that depends on this d hat. And then you do your dual update like how you did before. And then you check this condition, which depends on the iteration count. If the iteration count gets too big, then you actually restart with a larger estimate for the diameter, and then you go back to this initialization phase. So essentially, when you execute an initialization, it's called a restart. And for the next restart cycle, you could use the last primal iterate from the previous restart cycle, but you have to use the same initial dual multiplier, which is not necessarily the best thing to do, but you could prove that this algorithm provably converges. So what you would actually do in practice is you would allocate a large number of iterations for this guess t hat p naught to start off with, and then you would be actually conservative with your estimate for the diameter. And you actually find that you don't restart that much if you do something like this. You don't need such an accurate estimate of the diameter to actually get convergence in practice. This is more for a theoretical result. You can prove that you also achieve this 1 over epsilon number of resolvent evaluations to get approximate KKT point. And it's parameter free. No knowledge of the diameter is required anymore because I essentially did this guess and check kind of procedure for the diameter. If something goes wrong, then I increase my guess for the diameter and then I restart. So each time I restart with a larger guess for the diameter. And I can do warm restarting for my primal iterate. The initial primal iterate for the next restart cycle can be the one from the previous one, but initial dual multiplier must be the same for every restart cycle, cold restarting, to get the complexity to work out, to bound all these complexity of all these restart cycles. So now I wanted to develop something more practical because those other algorithms were more for getting optimal complexity. So I considered the same problem, but now instead of assuming strong duality, let's assume this stronger condition that there's some point in the interior of the domain. So this script n is the domain of PCIN such that it satisfies the linear constraints. And I also assume that PCIN is Lipschitz continuous. And can I develop a more practical method? I can under these conditions that also achieves a 1 over epsilon rate. You can, under weaker conditions, you can develop an adaptive method, but you get a worse rate. So now I developed this OPF ALD method, which is optimal, adaptive, parameter free, and also get this thing, complexity guarantees that are stronger. They're now on the last iterate as opposed to the best iterate. And I use an adaptive tolerance to solve the augmented Lagrangian subproblems, and I can use adaptive penalty, like provably. So this is what you do. It's a little complicated maybe, but so you start off and you check if primal feasibility is small. So if AZK minus 1 minus B is actually less than or equal to epsilon, then you want to actually set epsilon k hat to be epsilon. So epsilon k hat is the tolerance that I'm going to solve my augmented Lagrangian subproblems with. So if primal feasibility is satisfied, what I'm saying is that I'll solve the augmented Lagrangian subproblem very accurately to epsilon. But if it's not, then I'll set epsilon k hat essentially to epsilon tilde k. And epsilon tilde k is something generated by the algorithm. So you could start off with epsilon tilde 1 to be something big, like 100 or 50. And you call the AR method with this tolerance epsilon hat k. So you do this, so it won't necessarily always be epsilon, which could be very small, could be something much bigger. And then you, again, do your dual update, and then you check if RK is less than epsilon and primal feasibility is less than epsilon. Before, I didn't need to check if RK was less than epsilon because I always drove RK to be less than epsilon from step 2 using the AR method. But now I'm using a different kind of tolerance. And then in step 4, you can update your penalty to be 2 times of what it was previously, and then you can reduce your tolerance by 2. So you can start off with an epsilon tilde k, which is very big, like 100, and then, so this is what I actually found in practice when I was working on SDP. When coding it for the first augmented Lagrangian subproblems, you don't want to solve them very accurately, and then you want to solve it more and more accurately as you go. So you can start off with epsilon tilde 1 to be 100, then epsilon tilde 2 to be 50, and then this seemed to perform better than doing something else. So here's my outer and inner complexity results. So the number of outer iterations you perform is at most this log 1 over epsilon. And again, this is the outer iterations is the ones indexed by k. And in other words, you get this convergence on the last iterate. So you see that this is AZ capital K. It's not the minimum anymore. So I get this kind of stronger guarantee, which I call last iterate convergence. And the number of inner iterations that you do to solve your AL subproblems by AR method is this square root 1 over epsilon, essentially. And then this 2k minus 1 is something that shows up from the penalty parameter. And so you get this complicated bound, which you don't actually multiply 20 and 21 to get the complexity bound because you'll get a log, and you don't want to get logs, so you have to actually do a careful summing, and you get some geometric series, and you don't actually get this log to show up because I didn't want to get log. And it turns out you get 1 over epsilon total resolvent evaluations if you do this carefully with no log. So I get this 1 over epsilon complexity now, and it's fully parameter free again, and I use adaptive tolerance and penalty in my algorithm, and I get convergence on the last iterate as opposed to the best iterate. So I just briefly talk about this because I don't have too much time, but I also consider the case where PCI is mu bar strongly convex. Well, before I was just assuming convexity. And I developed this fully parameter-free AL method, which achieves this bound epsilon minus 1/2. But now I have this logarithmic term of 1 over epsilon to the 4th. But the lower complexity bound is, for finding primal solutions, is epsilon to the minus 1/2. So there's this bit of a gap there. And the best known upper complexity bound I could find was epsilon to the minus 1/2 log 1 over epsilon. So their complexity is a bit better than mine or ours, but their method is not parameter free as it requires knowledge of mu bar, but I don't require knowledge of mu bar. So I get these extra terms that show up in the log to make my method parameter free. But if I had a parameter dependent algorithm, I would also get this same bound as this Lu in my paper log 1 over epsilon, but I don't know how to remove the log in this setup. Using the technique that I use for the convex case doesn't work here. The best bound that I could get is epsilon to minus 1/2 log 1 over epsilon. So I think this seems to be still open, a still open question if you're interested in these kind of things. So I guess I have like 20 minutes to talk about SDP now. So we come up with this method which we call HALLaR. It's for solving SDPs. So this in P, this is just a special case of what I talked about before. So now we minimize a linear function subject to linear constraints, and X is in the spectraplex, which is in 22. So it's the intersection of a trace constraint and the PSD cone. So we have this trace constraint to make our feasible region compact, because you'll see we'll do some sort of Frank-Wolf type of method. And you can write the dual of P in this form. You associate Lagrange multiplier P with the linear constraints and the theta with the trace constraint. And we assume this strong duality type condition holds again. So what are the computational considerations for solving huge SDPs. So projecting matrices onto this spectraplex, it can be expensive because you require full eigen decomposition. So you wouldn't want to do like the methods that I showed in the first half of this talk, because those are all projection type methods or accelerated type methods. So instead, we only compute minimum eigenpairs of structured matrices because we do Frank-Wolf. And also, another thing that you wouldn't want to do is project onto this affine manifold. And since we do augmented Lagrangian, this primal dual method, we never compute this projection, and most methods don't either. And then this is like, the main issue is how do I store this n by n matrix? It requires a large amount of memory. So we tested on my computer. And a personal laptop with 32 gigabytes of memory can only store a fully dense X where n is 65,000. And if you try to create a matrix that's larger, you'll get an out-of-memory error. So we addressed this issue by using this Burr-Montero low-rank factorization scheme, where all the iterates have the form UU transpose, where U is hopefully some skinny matrix that's n by R, and hopefully the number of columns R is much less than n. And we only store U, and we never store this whole matrix X. Prior work on spectral bundle methods, they made progress in circumventing these first two issues, but the issue to address this memory issue to solve larger SDPs was this low-rank idea by Burr-Montero. So what is this low-rank idea? So Montero told me that it was what they were inspired by were these results by Barvanok, Pataki. Shapiro, Barvanok, and Pataki showed that SDP has a solution of low rank. So there exists some solution, optimal solution X star with rank X star, with rank R star that's less than square root 2m, where m is the number of constraints. So what did Burr-Montero propose to do? They proposed to do this factorization X equals UU transpose, where U is an n by R rectangular matrix where R is chosen carefully. So when you do this, you restrict SDP matrices you restrict SDP to matrices of rank R. So now you get this PR, which is a QCQP. You turn your trace constraint to this Frobenius constraint. And the advantage is that U has n by R entries, while before I had n times n plus 1 divided by 2 entries. But now you made your problem non-convex, and finding global optimum is MP hard. So if you had R large enough, greater than some R star, then find global optimum. This problem is equivalent to finding global optimum of the original problem, but this is MP hard. And also PR may not be feasible. So in general, Burr-Montero has limited complexity guarantees, but people have been trying to understand the landscape of the non-convexity in PR. And it turns out that if R is greater than or equal to square root 2m, which is like this kind of Pataki bound, then non-convexity is benign for PR. So if you found a local minimum, then almost always you found a global minimum of PR, and you found a global minimum of the original problem. So this is some nice result done by Beaumont. What is our method? So we don't factorize the SDP right away and make it non-convex. Instead, we do augmented Lagrangian, like how I was doing before, but I factorize the AL subproblems. So as you can see here, I generate my primal iterates xt to approximately minimize the augmented Lagrangian function, and then I do my dual update. And how the main workhorse for creating a method that performs fast is solving these subproblems very efficiently. So we use a low rank method to solve the subproblem ALT, which we might have to solve 100 or 200 times. So I'll mainly be talking about how do we solve the augmented Lagrangian subproblems, which are solved over this spectraplex. It's a trace constraint intersected with the PSD cone. And so we never actually generate xt. We only generate it in factored form yt transpose. We only generate yt, so we never form this huge matrix. And hopefully the number of columns of yt is much less than n. Yeah, so we never form this dense matrix xt. So here's an overview of the HALLaR method. So HALLaR method is for solving the teeth AL subproblem. So I'm talking about solving ALT. So we start off with some U0. It's the global solution found from the previous AL subproblem. So we do this warm restarting, and it's in n by R1. So R1 could be like 10 because the rank went up to 10 for the first AL subproblem. And so now we start off in this n by rk space, so it's indexed by these indices k. And what we do is we restrict the AL subproblem to the space of matrices in n by rk. So we factorize ALT to be in n by rk. And we get rid of this trace constraint. It becomes the Frobenius ball of radius 1. And now we have a quartic over the ball, because when you replace x here by UU transpose, you get this quartic because of this quadratic term that shows up in the augmented Lagrangian. So we use this method that we came up with in the previous paper to minimize this non-convex problem over this ball. And then we check if the stationary point we found U tilde k transpose is near globally optimal for the convex AL subproblem. And to do this, you don't actually have to form U tilde k transpose. You can check the condition with just forming U tilde k, and I'll show you how. And if it is near globally optimal, then we set yt to be this U tilde k, and we use this as our initial point for the next AL subproblem, so warm restarting. But if it's not near globally optimal, then maybe we ran into some weird stationary point or some bad point. So we perform Frank-Wolf with respect to the AL subproblem, a U tilde k, to obtain uk. And typically when you do this, Frank-Wolf does these rank 1 updates, so you actually increase the number of columns if you iterate by 1. So then when you go back to step 1, we do this alternating procedure. Now you're in n times rk plus 1 space. And then you restrict to this space of matrices, and then you try to find a stationary point again, and then you keep going back and forth between these two steps. So just some simple remarks. So in step 1, when you do this non-convex solve, they all have rk columns, the iterates generated by the non-convex solver adapt AIPP. So that's not changing the rank in any way. But when you do Frank-Wolf step and obtain uk, you increase the number of columns from rk to rk plus 1. It can all drop all the way down to 1 because of some technicality, but it's unlikely. So what happens in practice, though, is actually many AL subproblems can be solved with a single iteration of HALLaR. So what does that mean? It means I restrict to the space of matrices in PK, and I find a stationary point, and then I check if the stationary point is near globally optimal for the convex AL subproblem, and it turns out almost always this is the case, and no Frank-Wolf steps have to be performed. This is typically the case for the first 100 to 150 AL subproblems, but as the penalty parameter grows, the subproblems get harder to solve, then you do more and more Frank-Wolf steps, and you see the rank grows later on in the algorithm. And then so here's another way you can interpret our HALLaR method. You can interpret it as like a modified Frank-Wolf method where our non-convex solver just acts as like a spacer step. It makes the objective value better than that of its input. So really, it's just something that was good for computational performance, but the convergence is driven by Frank-Wolf. And then another interpretation is we compute this sequence of stationary points by our non-convex solver, and then we use Frank-Wolf steps to escape from these bad stationary points that we might have found in step 1. So now I'll just go over some more technical details quickly. So we use this non-convex solver, which we call adapt AIPP, to solve these quartics over balls. And it's an inexact proximal point method, which is parameter free. And we developed this in some previous paper from several years ago. So what is this adapt AIPP method? It's a proximal point type method. You add a quadratic here, and then you approximately solve these regularized subproblems using some kind of FISTA method. And then you keep iterating, and then you update your proc center to be VI. So maybe this is confusing, but it's a double-looped algorithm to solve these subproblems in PK. So I think it's interesting if you can develop something faster to solve these PK. We tried some direct methods that are not like double-looped, but just single-looped methods, but they don't seem to perform as well. But I think you could develop something better than this. So we use this adaptive version of FISTA to solve these regularized subproblems. So if you take the lambda small enough, then actually these subproblems are strongly convex, but because you're weakly convex, and then you add this quadratic, then you're strongly convex, but we don't actually have the lambda small, we allow it to be big. And this is actually very important for how it performs in practice. So after we get this stationary point from solving the non-convex subproblem, this U tilde k, we check if U tilde k transpose is optimal for the augmented Lagrangian subproblem. And to do that, we have to compute an eigenpair of this gradient. And then this lambda k, vk min, and then theta k and uk depend on these different quantities here. And then we check this condition in this second bullet point, and we check if it's less than epsilon. So what is this condition? This condition is just checking if 0 is in the gradient plus the epsilon normal cone of the spectraplex. So this is actually equivalent to checking if Frank-Wolf gap is small, if you know what that is. And you see we don't actually have to form U tilde k transpose to do this. We just have to compute a minimum eigenpair of this gradient matrix. And to do that, we just do matrix vector multiplications. And if you do all the math carefully, you'll see you don't actually have to form this matrix. So what is this UK transpose? It's just solves the linear minimization oracle because we're doing Frank-Wolf. And the spectraplex has rank 1 extreme points. So now that I checked, so you check the condition. If this Frank-Wolf gap is small, then you stop. If it's not small, then you perform a Frank-Wolf step. And the Frank-Wolf step, so alpha k is how you compute the step size. And the Frank-Wolf step is done in 24. So you can see that when you do a Frank-Wolf step, you're just adding a column. You're adding this UK. So really, I'm generating UK so that UK transpose can be seen as the iterates of Frank-Wolf in the X space. But I'm only forming UK. Yeah, so you're adding a column essentially, which is UK is this is the thing that solves this linear minimization oracle. It's this minimum eigenvector. And then just a comment that this step size alpha k for our SDP has a closed form solution, and this step size seemed to perform best for us in practice than using some kind of decaying step size that people use in Frank-Wolf type algorithms. We tried that, but it didn't give us as good results. So that was a lot of equations. So here's just the algorithm in pictures. So you restrict to this space of matrices, and you get a non-convex problem over a ball, and you try to find a stationary point. But the stationary point might not be optimal for my convex AL subproblem. You might have some bad stationary points. So you escape the stationary point using Frank-Wolf steps. Frank-Wolf steps take convex combination of your current iterate and extreme points of your feasible region. And the extreme points of your feasible region are these rank 1 matrices, right? So you're doing these rank 1 kind of updates. So Frank-Wolf steps just increase the rank. You append a vector to your matrix, a single column, which is this minimum eigenvector, essentially. So here's our theorem of our whole algorithm. So we achieve this complexity bound. So our goal was not achieving optimal complexity bounds in this work. It was to solve these bigger SDPs. So we get this 1 over epsilon squared number of eigenpair computations to find this approximate KKT type solution, primal feasibility, dual feasibility, and complementarity. And it turns out we actually have to do epsilon to the minus 2.5 number of gradient evaluations in the factorized space, but I don't show that there. So I guess I have a little bit of time, so I now go over the computations. So we compared against a lot of different methods. So there's CSDP, some interior point method where we got the code and we tested it. Cosmos an ADMM type method. And then SDP-HALLaR is the original method by Burr-Montero. SDP-NALL+ is some Augmented Lagrangian method. They solved the AL subproblems using semi-smooth Newton. And then Thin-Segal is similar to our method in the regards that they do Augmented Lagrangian, but they just do Frank-Wolf. They don't use the non-convex solver. And then so they keep increasing the rank. And that's actually what we started off with when we started on this project, but it doesn't perform as well because the rank ends up increasing a lot. And then there's these sketchy methods by Yurt-Sever where they work with the sketch of the matrix in some like projected type space. And there's this more recent work, Mani SDP, where they also factorize the augmented Lagrangian subproblems, but they solve them using Riemannian trust region method while we use our proximal point type method. And they also have a different way of increasing the rank while we use Frank-Wolf steps to increase our rank. So I'll go over this maximum stable set problem. So given a graph, maximum stable set consists of finding largest set of vertices so that no two of them are connected by edge, can be formulated as this IP in 27, and it has this SDP relaxation by letting E be the vector of all ones. So we solved the SDP relaxation in 28. And this is the results that we get. So our method's on the left, and these were smaller graphs. So V is the number of vertices, E is the number of edges. So these were all like less than 70,000 or 140,000, and we solved all these in less than a minute. The columns 2 through 4 all based off Frank-Wolf. And the star means that they didn't terminate in the time limit of 3 hours, because I was trying to find a 10 to the minus 5 accurate solution, but they found 10 to the minus 1 or 10 to the minus 2 accurate solution. And CSDP is this fifth column. It does well for the first few problems, but when you get to larger dimensions, it crashes. This interior point method. And then Cosmo also crashes, and this SDP-NALL+ eventually crashes as well. So the double star means that my computer ran out of memory, and I had 32 gigabytes of memory. So we wanted to see how large problems we could solve. So we can solve these huge problems because these huge problems have low rank. We can't solve any huge problem to high accuracy, but we can solve these ones to 10 to the minus 5 accuracy. And the biggest one we were able to solve had 17 million vertices and 201 million edges, but the solution had very low rank. It was not more than 10. Or sometimes 20 for these problems. And if you wanted to solve bigger problems, but the solution had higher rank, then from testing the code, maybe the best you could hope for is 10 to the minus 2 or 10 to the minus 3 accuracy. But you cannot solve all of them to 10 to the minus 5 accuracy. So we did this comparison with the Burr-Montero method and Mani SDP, and we were sometimes around 300 times faster then then the code by Sam, and this Mani SDP code, and these weren't too big problems. So another problem we consider is this phase retrieval problem. So you're given some M pair of measurements, and you want to retrieve a vector that satisfies the linear measurements. So it has this SDP relaxation by forming this complex Hermitian matrix. So we solved this problem here below. And we were able to solve all these problems in less than 12 hours. Largest problem we were able to solve had 3 million, was the size of the matrix variable, and 38 million was number of constraints. And these other 3 methods were based off Frank-Wolf. They don't crash, but they don't converge to the accuracy of 10 to the minus 5 within 4 hours. So if we altered our method as well, and we got rid of the non-convex solver, and we just did Frank-Wolf, the rank increases much more, and we probably won't be able to solve these problems in the time limit as well, from what I observed, because the rank increases exponentially more if you don't have that intermediary step of restricting and using the proximal point type method. So you actually see, if you look at the rank of the solution that this last code outputs, it's much higher than what we got. It seemed to miss the solution of low rank. And like I say, if I modify our code to do that as well, we also miss the solution of low rank for some reason. So I consider this matrix completion problem as the last problem. It has this nuclear norm formulation, and we consider this SDP formulation, and we solve the SDP. The largest problem we were able to solve, the N was 200,000, the M was 22 million, and we solved this less than 5 hours. But now we have some better results where we can go in a few more million, because we have a working code that's a GPU implementation. And so we're working on creating a GPU implementation of our code. So the conclusion is that we've developed this solver, HALLaR, for solving huge SDPs, and we can solve SDPs with dimension pair on the orders of millions in under a few hours if they have low rank solutions. So sometimes you can't do it to high accuracy if you didn't get lucky and there was not a low rank solution. So it's based on a bunch of these papers. So thank you.